Okay, so this is our fourth problem on related rates. So here's the problem. A hay baler makes cylindrical bales of hay. The machine squeezes the hay in while adding new hay or removing it. At the moment the bale's radius is 0.6 meters. The radius is decreasing at a rate of 0.1 meters per second. At the same moment, so when the radius is 0.6 meters, the bale's height is 1.2 meters, and the volume of the bale is decreasing at a rate of 0.2 meters cubed per second. At this moment, when the radius is 0.6 and the height is 1.2, how fast is the height of the bale changing? Is it increasing or decreasing? As always, first step, let's draw a picture. What are we talking about here? We're talking about making a cylindrical bale of hay. So draw a cylinder. So we have a cylindrical bale of hay, and we're told that the radius is changing, the height is also changing. So we have our two key variables. The radius of the hay, of the bale, we can call r. The height we can call h. And the volume we'll call v. So let's say v is the volume of this bale of hay. Let's write down now what we know about these three variables: the radius of the bale, the height, and the volume v. And notice that all of the three variables are functions of time. Time is the independent variable, and as time changes, the radius will change, the height will change, and therefore obviously the volume. So what do we know about these three variables? At the moment the bale's radius is 0.6 meters, so when r is 0.6, the radius is decreasing at a rate of 0.1 meters per second. That's the rate of change of the radius, that's the derivative of r with respect to t. Specifically at the instant, at the moment when the bale's radius is 0.6. So when the radius is 0.6 meters, the radius is decreasing at a rate of 0.1 meters per second. So because it is decreasing, since r is decreasing, it means that its rate of change is negative, and that's negative 0.1 meters per second. At the same moment, so when the moment is that r equals 0.6, the bale's height is 1.2 meters, and the volume of the bale is decreasing. That's the rate of change of the volume. The volume of the bale is decreasing at a rate of 0.2 meters cubed per second. And that moment, as we've just said, is when the radius is 0.6. But we were also told an additional piece of information. At the same moment, when the radius is 0.6 meters, the bale's height is 1.2 meters. So when r is 0.6, the height is 1.2. The volume of the bale is decreasing at a rate, that's the rate of change of the volume. It is decreasing, therefore, the implication is that we have a negative rate of change, and the rate is 0.2. And since we're talking about volume, meters cubed per second. Now we have what we know. Here's what we want to find out. At this moment, well, this moment is the moment in time when the radius of the bale is 0.6 meters, the height is 1.2. How fast is the height of the bale changing? Well, how fast is something changing? That's the rate of change. That's just the derivative. So we want to know the rate of change of the height of the bale of hay at this moment, specifically when the radius is 0.6 meters and the height is 1.2 meters. So now we can forget the word problem. We have a complete translation of the situation. We have a picture where we have labeled the key variables of interest. We have the rate of change that we know, and we know the rate of change that we are trying to find. What we need now is a relation. We know the rate of change of r, the radius, and the rate of change of the volume of the cylindrical bale of hay, and we want the rate of change of the height of this bale. So we have to relate the height with the volume and the radius of the bale. Well, we know the volume of a cylinder is simply the area of the base. This is a circle of radius r, so the area of the base is pi r squared times the height, times h. And now we have a relation. We have related v with r and h. And keep in mind again that r is a function of t. H is also a function of t. And the volume also is a function of t. So as the previous three problems, the independent variable is the time t here in seconds. And all of r, h, and v are changing as functions of time. And so we have three functions of time. Now here we have two options. We want the rate of change of h, so we could solve for h in our relation and then differentiate, and we'll have to use the quotient rule, or we could differentiate the relation as is and then solve for dh over dt. Whichever way I'll let you choose, and you can try the other way if you want. Here, I'll solve for h, and then I'll differentiate the expression. So if the volume is pi r squared h, this means that the height will be the volume divided by pi r squared. And now here, I could differentiate this as is, but I'll simplify a little bit, because the over pi is a constant multiple. So you can factor this as 1 over pi times the volume over r squared. So when you differentiate this, you'll just leave the 1 over pi up front, as it is a constant multiple of the function of t. Now here you have two options. You could use the quotient rule in finding the derivative of this, or you could write 1 over r squared as r to the minus 2, and avoid that way the quotient rule. Whichever way you choose is equivalent, but I'll go here with avoiding the quotient rule in favor of the product rule and the power rule. And this will be my final relation. So I'll go with the height is 1 over pi times the volume times r to the minus 2. And this is the relation I'll use to find my derivative. Okay, so because h is a function of t, this is a function of t. Because v and r are two functions of t also, the right-hand side is a function of t. Well, both sides are equal as functions of t, therefore they have the same derivative with respect to t. Let's differentiate. The left-hand side is easy. It's just dh over dt. That's equal to, well, here we have 1 over pi times this, but as we've said before, 1 over pi is a constant multiple, so we'll just stay 1 over pi. So that takes care of that. Times, and here you have to be careful. This is v times r to the negative 2. So you have to use here the product rule. So the derivative of the first function with respect to t will give you dv over dt. And keep in mind that the 1 over pi multiplies the entire derivative of the expression. So make sure to open your brackets. So dv over dt times the second function, r to the negative 2, plus the first function v. And here you have to be careful. You differentiate r to the negative 2, but not with respect to r, but with respect to t. So be very careful here with the chain rule. We have r to the negative 2. The outside function is the power negative 2, so we bring it down, times negative 2. Negative 2 minus 1 is negative 3. Of what? Of what's left over, r. But there is an r left over. So we have to multiply what we have so far by the derivative of what's left over, and that is dr over dt. And this completes the differentiation of the right-hand side. We can write this in a slightly simpler form. dh over dt is 1 over pi times the derivative of the volume with respect to t. If you prefer here, if you want to drop the negative exponent, write this as 1 over r squared. Same thing. Plus, well, I should have said minus, right? Minus 2v. And if you multiply by r to the negative 3, if you want the positive exponent, that's just 1 over r cubed. So negative 2r over r cubed times dr over dt. So it's this minus this, and the whole thing times 1 over pi. If you wanted here, you could factor 1 over r squared, but let's not do that here. Now, well, we have the h over dt, but remember, we wanted the h over dt specifically when r was equal to 0.6 meters and h was equal to 1.2 meters, right? So let's evaluate now. We'll move on to another page. Let me just recopy what or do this. A little simpler, actually. So here's what we had. dh over dt was equal to this, but we wanted dh over dt specifically when the radius was equal to 0.6 and the height of the bale was 1.2 meters. So let's substitute now. 1 over pi is always 1 over pi times, well, dv over dt, when r is 0.6 and h was 1.2, if you remember, dv over dt at this instant was negative 0.2. This is negative 0.2. And we multiply by 1 over r squared, so we divide by the radius squared. But the radius is 0.6, so it's over 0.6 squared. And then what? Minus 2 times the volume, so minus 2 times the volume. But if you remember, this was the volume of the cylinder. The volume is pi r squared times h for any r and h, but here r is 0.6, h is 1.2, so we'll substitute. The volume, as we've just said, is pi times the radius squared, 0.6 squared, times the height times 1.2. And that's the volume of the cylinder when the radius is 0.6 and the height is 1.2 over r cubed 0.6 cubed. And finally times dr over dt. At this instant, let's go back up. dr over dt at this instant was negative 0.1 meters per second. So it's times negative 0.1 meters per second. And now we just have to compute this. Well, let's simplify a little bit the expression here. 0.6 squared over 0.6 cubed will give you 3 minus 2, 1. So you're left with a single 0.6 on the denominator. And now we can evaluate the expression. Take your calculator, find this, and then divide by pi, and you'll have the answer. Of course, we'll have here an approximate answer. And we get approximately, after you compute all of this, divide by pi, you'll get approximately 0.223. And of course, what we have was the rate of change of the height with respect to time. The height is a variable of length, so this will be meters per time in second. So 0.233 meters per second. And that is our conclusion. So when the radius of the bale is 0.6 meters and the height is 1.2 meters, the rate of change of the height is approximately 0.223. And remember that we were also asking for the rate of change of the height as a function of t at this instant, but also is here the height increasing or decreasing at that time? Well, we have a positive rate of change, and a positive rate of change means that the derivative is positive, therefore the slope of the tangent line is positive, therefore the function is increasing. So the height is increasing at this time. So when the radius is 0.6 meters and the height is 1.2 meters, the height of the bale is increasing. And increasing at what rate? At approximately 0.223 meters per second.